In this lecture, we're going to look at how we can use the Grignard reaction to synthesize or propose the synthesis of complicated alcohols. This skill set is going to seem new, but it's really just building off of what we have already talked about related to the Grignard reaction. So what I want to do is, I realize I haven't shared my screen with you yet. Sorry about that. Okay. What I want to do is say, let's propose a synthesis. Of, and let's pick a molecule. How about this? Yeah, that'll work. Okay, let's just make it simple. Simpler, excuse me, not simple necessarily. Propose a synthesis of this using a Grignard reaction. Okay, so we first have to recognize is that this molecule is an alcohol. Okay, we make alcohols using the Grignard reaction. You know what? I'm going to change the order of this. I'm going to make this lecture 106. We'll talk about alcohols in 105. Okay, so we make alcohols using the Grignard reaction, and it's a very powerful way to do so. So I'm saying let's make this particular alcohol using the Grignard reaction. So how do we approach this? Well, an interesting way that actually led to a Nobel Prize is called retrosynthetic analysis. Okay, in retrosynthetic analysis, what you do is you work backwards. To work backwards, what I'm saying is let's start with the product that we want to make and look at some bonds that make the most sense to make last, and then second to last, third to last, and all of a sudden you're at some starting materials you can run away with. Okay, so if we have this molecule, what I'm saying is let's go back in time and say, how would we make this? Well, what we could recognize is that with an alcohol present, maybe we just combine some carbonyl and haloalkane under Grignard conditions. How would we make this? Using a carbonyl and haloalkane under Grignard conditions. Well, it turns out that to go directly to this product, there are two approaches. And the approaches are kind of depend on which CC bond you want to make. Okay, let's look at that on the next page. Let's look at both of these approaches and see how we would use this to handle the synthesis of this complicated alcohol. Okay, so we have our molecule in front of us. And what I want us to recognize is that if we're going to define some carbonyl and haloalkane combination, first, let's look at the carbon that's attached to the oxygen. This must be the carbonyl carbon. Why? Well, that's the only carbon that's attached at all to an oxygen. So as you're identifying carbonyls and haloalkanes to mix together under Grignard reaction conditions, what we have to first recognize is that We know something already about the starting materials. That must be our haloalkane. Now, what we could do is we could break here. I'm going to make that green. I don't know why that's bothering me. Okay. We could break here or here. This is a potential new bond. And I said break. I should be careful. Potential new bond. So in retrosynthetic analysis, what we do is we work backward through what we call strategic disconnections of the desired product. We say, okay, desired product, it makes the most sense strategically to work backwards and disconnect the molecule at these particular sites. Let's look at that in more detail. So, I'm sorry, I'm redrawing this so much. We have our molecule. We have our carbonyl carbon. I'm going to say that this is our strategic disconnection. I'm going to disconnect the product at this bond and say that's the bond I will make using a Grignard reaction. This is the bond to make under a Grignard reaction. Okay, so let's do this. Let's work backwards then and say, what are the two things that I am going to mix together to give rise to this alcohol? Okay, now first of all, what I'm introducing is this kind of double line, single-headed arrow. This is called a retrosynthetic analysis arrow. Lots of arrows, I get it. This is the field we live in. I mean, this is organic chemistry. A lot of curly arrows, reaction arrows, equilibrium arrows, resonance arrows. Okay, but this kind of double-lined, single-headed arrow, that is, I don't know what this was. Okay, whatever. That is a retrosynthetic analysis arrow, and it's saying we are going to cut our product at these positions. Now I'm saying we're going to mix two things together, and I'm going to give myself some space over here. We're going to mix two things together that would give rise to this final product. So the retrosynthetic analysis arrow is working backwards just to help us kind of organize our thoughts. If we do that, we see that one piece has the oxygen. That's going to be the carbonyl. The piece that has the oxygen and the carbonyl carbon, which I've indicated with that dot label on our carbon, that's going to be the carbonyl in our strategic disconnection. We pull the molecule apart and we say, we're going to make the bond that I've indicated in green. That's where the bond we're going to make under a Grignard reaction. Well, for that to work, we need to use the carbonyl that I've got outlined. And then the other molecule, the cyclobutane, or the square, is actually going to be our Grignard reagent. That's going to highlight that this atom right here, this is our, I could draw a better arrow, sorry. That's our nucleophilic carbon. Okay, so for us to make this alcohol by way of a Grignard reaction, we work backwards to see that it would have to arise from these two reactants by way of a Grignard reaction. Now, additionally, what we can do is we can work backwards again from the Grignard reagent. That is to say that if I have this molecule as my Grignard reagent, how would I make this molecule? Well, we know how to make this molecule. This is a Grignard reagent. And I'm going to show a retrosynthetic analysis arrow getting me back to my starting material. So how would I make this? I would take Mg0 and react it with some haloalkane to give rise to the Grignard reagent shown on the left. The haloalkane is simply the square, or the cyclobutane, with a bromine attached to it, because the magnesium, we know that to make a Grignard reagent, we just take magnesium 0 and plop it between the carbon and the bromine atom. Now at this point, we've reached two good starting materials. So, and by good, I mean accessible. I'm going to highlight those in yellow, and magnesium, sure. These are our accessible starting materials. So we worked backwards to get to our accessible starting materials using retrosynthetic analysis. Have we solved the problem? Okay, what was the quote problem or the thing we wanted to do? The thing we wanted to do was to propose a synthesis of this alcohol. We have not done that. All we have done is organized our thoughts using retrosynthetic analysis. So our proposed forward synthesis, which is going to have to go on the next page for me, and I put forward in quotes here, proposed forward synthesis is going to actually be what things were mixed together and under what conditions to give rise to the alcohol that you wanted to obtain. Okay, so the proposed forward synthesis, and I use the word forward because that's in contrast to the retrosynthetic analysis that was working backwards. So our proposed forward synthesis, and this is honestly, students get tripped up here, but everything is right in front of you. The carbonyl, the haloalkane, and the magnesium, these yellow things that I've highlighted, accessible starting materials, this is everything that you need for your forward synthesis. So all I'm going to do is take those pieces and plop them together under what looks like a typical Grignard reaction problem. And I already know what the product is. So let me say that again. I'm going to take my haloalkane and my carbonyl. These are things that were on the, we know these things. It always bums me out when students can do the retrosynthetic analysis, not the forward synthesis, because all we're doing is taking what we just did. Our haloalkane, which we identified previously, our carbonyl, which we identified previously. And then, I mean, after you practice this enough, I don't think it's too hard to just remember that what goes over the arrow is magnesium 0, carbonyl, and then H plus for the quench. Okay, you could even put diethyl ether as your solvent. This is how I would make the molecule in question. Proposing a synthesis is I would have that haloalkane mixed with that carbonyl. Step 1, add the magnesium 0. Step 2, add the carbonyl. So I guess, add the carbonyl second, but that's indicated in the arrow. Step 3, add H plus to quench the reaction. Now, what product do we get? Oh, Willoughby, this is a predict the product question. No, it's not. The question was, propose a synthesis for this molecule. We know what the molecule is. This is simply an organize your thoughts, synthesize the information by showing me that you can synthesize the interesting molecule. Okay, so it's just a strategy. Retrosynthetic analysis is just a strategy, but it does all of the heavy lifting so that when you propose a forward synthesis, all you're doing is realigning everything that you wrote in your notes. To get these questions right, you will need to propose a retrosynthetic analysis along with your forward synthesis. Please note that a lot of things will be, if we're doing Grignard reactions, will be redundant, right? I mean, once we identify the strategic disconnection, we just have different things drawn attached to bromine and attached to our carbonyl, okay? Now, what I mentioned was there were 2 possible strategic disconnections, and that's because I think that's true for the most part. There might be some examples, but if this is our carbonyl carbon, an alternative strategic disconnection could have been over here. And remember, strategic disconnection is just us saying this is the CC bond to make. So I'm going to make that CC bond instead of the other one by way of a Grignard reaction. To do that, I'm going to rely on retrosynthetic analysis to tell me what my combination of Grignard reagent and haloalkane should be. So what we have here is, like, we have kind of 2 halves of our molecule. We have the half that has the oxygen, right? We have the half that has the oxygen, and let's delete this. And then the half that does not have the oxygen. So these are the 2 points. There's our circle. Maybe we want to put a star here. Those are the 2 things that we need to connect together by way of a Grignard reaction. So how do we get there? Well, step 3 is to add the hydrogen. So before we get there, we need to have a carbonyl that is an oxygen without a hydrogen and a carbon-oxygen double bond. So this is our new carbonyl. And that's half of our proposed synthesis, right, is finding the carbonyl. Now, the other half is how are we going to connect that to this 3-carbon chain? We could just add MgBr. Okay, this is our Grignard reagent. I cut the molecule in half along the line, along the bond that I wanted to make. Okay, I delete that bond because I'm going to make it as the last step. So I don't have it in my starting materials. I deleted the bond. I have 2 halves of my molecule. The half with the oxygen is always the carbonyl. The half without the oxygen is always the Grignard reagent. And the Grignard reagent, we can further work back to a molecule where the magnesium is no longer sitting between the carbon and the bromine. And so now we have our haloalkane starting material. And we have some, I'll go ahead and I'll write plus Mg0. Count for allyl atoms. And we have our accessible starting materials. So there's my retrosynthetic analysis, okay? It looks very similar, except we've just cut 1/2 over the other half. There's 2 bonds where we could do strategic disconnection. I could be super annoying and be like, well, your starting materials can only have 4 carbons or less, and I guess the carbonyl in this case has 5 carbons, so the other route is better. But you know, those things aside, what we have is just kind of 2 approaches that are highly similar. Both give rise to the product, and maybe you want to see that. We don't get points on this question until we propose a forward synthesis, right? You need to make the molecule. To make the molecule, you need to do the reaction in reality in the, quote, forward direction as opposed to the retrosynthetic analysis. So you might be kind of annoyed, like, why do I even bother with the retrosynthetic analysis? Well, all the work is already on the page, all right? If you want to do the forward synthesis, you take everything you drew for your retrosynthetic analysis and you just put it in the forward direction. I'm going to take my carbonyl, react it with my haloalkane. Doesn't matter which one I draw on the left or the right. And the first step of my Grignard reaction is going to be adding Mg0. My second step is adding the carbonyl, which is this molecule over here. And the third step is H+. So everything was part of my retrosynthetic analysis. What's the product? Do I have to predict the product? No. What we're looking at is just that you can organize your thoughts by way of retrosynthetic analysis. Otherwise, you just write down all the structures that you've already done and identified as part of your retrosynthetic analysis. The product of the reaction is the thing we started with. Okay, we worked backwards to our starting materials for the forward synthesis. Okay, so there's the forward synthesis, the retrosynthetic analysis, 2 retrosynthetic analyses for the exact same molecule. You can't have up to 3 if you've got an extra carbon present. I think it makes sense to have the pieces, the carbonyl and the haloalkane, to be about the same size. So this one's fine. The previous one I'd probably prefer, I guess, but no, you wouldn't. I can't imagine you would lose points, I should say. I haven't written the exam yet. But okay, so that's using the Grignard reaction to make complicated alcohols. We'll look at we'll kind of expand our toolbox beyond just the Grignard reaction to show how we can even make more and more complicated alcohols. Really powerful, but requires definitely shows the power of retrosynthetic analysis in organizing our thoughts, because otherwise things get so cumbersome. Like maybe you saw what the Grignard reaction would be by just looking at the alcohol, and that's fine, but you're kind of working backwards in your head. Let's just put it on paper. Okay, anyway, that'll do it for this video.